let's do that. Right, so couple of announcements first. So there are still a few people who haven't signed up on WebAssign. I think there should be a problem. A few people who have contacted me with difficulties, and we were able to work through them and get people actually signed up. So if you're having difficulty on WebAssign, please let me know. If you can, stay at the end of class today, and let me know what's going on, okay? So the plan for today is to discuss the dot product. So this is section 12.3 in your book. From last time, from vectors, when I asked you all, some people said they'd seen vectors before, some people had not. Probably the people who have seen vectors are likely to have seen the dot product, but not necessarily. So I know some of you might have seen this. I know some of you haven't seen it. Please make sure you pay attention especially if you've seen the dot product before, just so you're aware of exactly how the notation used by your textbook works. It's not always the same in every book. So just make sure you know what the ground rules are. All right, so I'm going to share my screen and we'll go through things. As always, if you have questions, just unmute yourself and let me know, or you can use the chat. If you tried the chat and I don't see it immediately, just unmute yourself and let me know there's a question. All right, come on. Here. Doesn't want to connect. All right, so let me try this again.
Hello.
Hello?
Mm-hmm.
Was there a question?
Hello. Yeah.
Okay, here's the screen. I hear some people there. If you have a question, please let me know. All right. All right, so we're talking about the dot product today. Okay, so we saw the basics about vectors last time. We know that we can add and subtract vectors. Remember, we work component by component when we do that. When we add two vectors, we add the components, corresponding components together. So the vectors have to have the same number of components for this to be defined. We can subtract vectors by subtracting the like components. We saw the scalar product, right? We know what to do if we multiply a vector by a number. We just distribute that multiplication by the scalar over all of the components of the vector. And there are a few other products, versions of multiplication that can be defined with vectors. So 12.3 talks about the dot product. In 12.4, we'll see another type of product called the cross product. Okay, and these two operations are important because they're actually related to things that we typically or frequently want to do when we're dealing with vectors. So there are geometrical interpretations of both the dot product and the cross product, which we'll talk about. So the basic definition right, we take the dot product of two vectors. Let's call the vectors u and v. And let's say that our vectors are in the vector space V2. So we're talking about vectors with two components. Okay. So we write this by putting the vectors next to each other with a multiplication sign in between. And for the dot product, we use a dot to represent the multiplication. So we're in V2, so our vectors have two components. And the way we define this is we multiply the corresponding components together. So U1 times V1, we multiply the first components, and then we multiply the second components, U2 times V2, and then we just add all of those results up. Okay, so that's the basic definition for the dot product of two vectors in V2 in two-dimensional vector space. There's a dot product in 3 dimensions. Right, we could have our vector A times a vector B, let's say. In 3-dimensional space, our vectors have 3 components. So B1, B2, B3. And the strategy is the same as we saw in 2 dimensions. We just add together the products of the corresponding components. So A1, B1 plus A2, B2 plus A3, B3. Okay, and that's about as much as I can fit on this screen. So does everyone have what they need from here before we move on? Good. Okay.
Could you wait a second?
Okay.
Okay, I'm fine.
Good,
Thank you.
good. All right. So in general, the dot product can be defined for vectors in any dimensional space you want. Okay, so in n-dimensional space, you could have vectors, and let me just go back to, I don't know, let's use X and Y. So n-dimensional space, each of these vectors is going to have n components. And the pattern for computing the dot product is always the same. You always multiply the pairs of corresponding components. So x1, y1, x2 times y2 in this case. Oops. All the way up to x sub n, y sub n. Okay, so notice the dot product is a scalar, a number. So the dot product is going to take two vectors that have the same number of components And the output of taking the dot product is a number, a scalar. If the vectors are not in the same space, if they don't have the same number of components, then the dot product is not defined. Okay, so some specific examples. Here's the dot product of two vectors in two-dimensional space, right? So first components are 1 and 3. Second components are 2 and 4. We do the multiplications and we get a result. If I have the vector 1, 2, and I try to take the dot products with a mismatched vector, this is just not defined. Okay, you don't pad the vectors with zeros so that you try to push them into the same space and then take the dot product. You've got the vectors 1, 2 that lives in the space V2, 2 components. 3, 4, 5 lives in V3. The spaces are mismatched. We don't have the same number of components. We cannot define the dot product. Is that clear to everyone? Okay, the basic idea. Everyone good? All right, so does everyone have what they need from this page of notes? Everybody good? Okay. So there are some general properties of the dot products. Oops. Properties. And I'm gonna assume here that I've got vectors A, B, and C in V3. Right, so they're going to be vectors with 3 components. And let's say D is a scalar. A number. The first property to note is that when I take the dot product of a vector with itself, what I really get is the square of the length of the vector. Okay, and that's easy to see. Here's if I say my vector A has components A1, A2, A3, take the dot product of the vector with itself, what I get is the sum of the squares of the components of the vector. Right, so that's A dot A. And the length of my vector A is the square root of the sum of the squares of the components, right? That's just Pythagorean theorem, essentially. Right, so notice that these two things are the same. Right, so just by directly calculating what these symbols mean, we see that the dot product of a vector with itself is the square of the length of the vector. In the same way, you can actually prove all of these properties that we're going to lay out here I'm not going to go through the detailed component by component calculation for each of these. But hopefully these are clear, and if they're not clear, you just write the vectors out and write out what's happening and make sure that you see where these are coming from. The second property to keep in mind is that the dot product is commutative. It doesn't matter if you take A dot B or B dot A. The order doesn't matter in the dot product. The result is the same. It's the same number. Okay. If you take a dot product with a sum of vectors on one of the entries, you can distribute that product. So this is going to, whoops, that should be a plus. This is going to be A dotted with B plus A dotted with C. So vector A dotted with the sum of the vectors B and C, I can distribute this multiplication over the addition. Okay, and again, you can see exactly where this is coming from if you just write out these vectors with general components. Make sure you're getting the same thing on each side of equation 3 there. The fourth property is, let's say we have a number D times our vector A. If we compute that scalar product and then dot that with a vector, that's equivalent to the scalar A times the number I would get by dotting A with B. And that's equivalent to A dotted with my number D times the vector B. Okay, so again, just compute each of these, and it's not too hard to verify that you get the same thing in every case. And then there's another fifth property, zero vector dotted with any vector A is always going to give you the zero vector. So remember, the zero vector is the vector all of whose components are zero. So that should make sense. You're just going to get a bunch of terms of the form 0 times a component of A. Each of those gives you 0, the number 0. When you add all those up, you get, oops, and that's not a vector here. That's the number 0. Okay, so these 5 properties are in the definition of the dot product are summarized for you right at the beginning of section 12.3. Make sure that you're aware of these rules, you're comfortable working with these rules. If you have to compute something that involves the dot product, sometimes it's convenient to use these properties to manipulate the calculation you're doing. You might want to reorder the vectors or so forth. Oops, sorry. So everyone have what they need from this page before we go on. Okay. So there's some geometry. Oh, and before I go on, I just want to make it clear here. We set up these general properties assuming that our vectors were in V3, but these properties hold if all of our vectors are in V2, if all of our vectors are in V4. In general, if the vectors live in the same space so that we can define everything that shows up here, these properties are going to hold in general for the dot product. Now the dot product in a sense, encodes some geometrical information about the vectors. Okay, and the theta here is the angle between the vectors. Okay. So here's the picture. We have in mind. Right, we've got our two vectors. We can form a plane that passes through our two vectors. And in that plane, we measure the smallest angle between the vectors, right? The angle that I showed here, not the angle here. And you can see where this is coming from with a little bit of work. There's a proof of this given in your book. And it's just a calculation, really. And it's based on the law of cosines. Can't draw. So let's just give names to these two things here. So let's say these are the two legs of the triangle, of a triangle. What's the vector that we could use to build the third leg of the triangle? Right, so can everyone see what we did here? Yes, so in the chat, we have the answer A minus B. Whoops, I'm mixing notations here. So A, B, A minus B. So hopefully it's clear to everyone that if I drew the arrow the way I did, right, it looks like the vector A plus A minus B. Well, that's not quite the way I drew it, right? If I add A plus A minus B, I would get 2A minus B. But you're on the right track, Jiwan. So if I drew this arrow in the other direction, then vector B plus vector A minus B I know that the B's would cancel and I would be left with the vector A here. Right, so depending on what direction you want this, the vector that represents the third side of the triangle to go, you could use either A minus B or B minus A. So is everyone clear on the idea of vector addition, vector subtraction? Okay, so we saw a couple different responses here. It doesn't really matter in this context whether you think of the vector going the vector A minus B or B minus A. The main point is that you have a triangle. the law of cosines is going to use the length of the sides, the lengths of the sides and in this angle. Okay, so, and I don't want to go through the calculation here, but the point here is that the dot product actually gets your hands on this information about the geometry of the two vectors. So you could manipulate that equation to get that cosine theta is A dotted with B divided by the product of the lengths of the vectors. Okay. And we can do an example. Let's say that vector A is, no. Let's say we've got 1, 2, and 3. We've got a vector B, which is 4, 5, 6. If I want the cosine of the angle, it's going to be A dotted with B divided by the product of the lengths of the vectors. So A dotted B with B will have 1 times 4 plus 2 times 5 plus 3 times 6. The length of the vector A is going to be 1 plus 4 plus 9. The length of the vector B is going to be 16 plus 25 plus 36. And this is going to be 4 plus 10 plus 18, so 28, 32. Square root of 14, square root of, let's see, 6 plus 6 is 12, plus 5 is 7. Carry 1, 4, 6, 77. All right, so assuming I did my arithmetic correct, this beautiful number is the cosine of the angle between the vectors, and we could work out the actual angle by taking the arc cosine, or the cosine inverse. And in general, that's not going to be any special recognizable angle, but in special cases, you might recognize what the angle is. Right, this is something you probably just need to punch into a calculator or punch into Mathematica to evaluate. Okay, so does everyone have what they need from the screen? Are you ready to go forward? Okay. There are some special situations, of course. We're often interested in whether two vectors are perpendicular to each other. Okay. Another word for perpendicular is orthogonal. Okay. And by that, we mean there's a right angle between the vector. So that means that the angle is 90 degrees or pi over 2 radians. And in general, remember in calculus, typically we prefer to work in radians, but you should be aware of the relationship between degrees and radians. If we measure all the way around a circle, that's 360 degrees or 2 pi radians. Okay, so there's a conversion factor. 360 degrees is equal to 2 pi radians. So if you have something in degrees and you want to convert to radians, you can do that, and vice versa, of course. So if our vectors A and B are orthogonal, let's think about what that means for the vectors. So A dotted with B is the length of A times the length of B times the cosine of theta. So that's going to be the length of A times the length of B times the cosine of pi over 2 radians. But what is the cosine of pi over 2 radians? It's 0. Okay, so someone in the chat gave me that. So you can check whether two vectors are at right angles to each other or are perpendicular or they're orthogonal, right? These are three ways of saying the same thing. By taking the dot product of the vectors, and if the dot product is 0, the vectors are orthogonal. If the dot product is not 0, the vectors are not orthogonal. Okay, so that's a fairly straightforward thing. Okay, so remember what the cosine looks like, what the sine looks like. This is theta. Y equals cosine theta. So special values of the cosine. Cosine of 0 is 1. The period of the cosine is 2 pi, so cosine of 2 pi, we're back at our starting point, is 1. Cosine of pi is -1. Cosine of pi over 2, that's right here, is equal to 0. Over here is 3 pi over 2. Cosine of pi over 4. Does anyone remember what cosine pi over 4 is? Oops, I think I'm. Anyone remember what cosine pi over 4 is?
The square root of 2 over 2.
Very good. So sometimes this is written 1 over root 2. Either of these are okay. So remember, you can get that by the Pythagorean theorem. If you have a right triangle with both legs of the triangle equal to 1, the hypotenuse must be square root of 2. these angles would both be pi over 4 for that special triangle. And the cosine of an angle like this in a right triangle is the adjacent leg divided by the hypotenuse. Right, there's another special triangle that's useful to keep in mind. Right, so if you start with an equilateral triangle, the sum of the interior angles of a triangle is pi radians. If each of those interior angles is the same because the opposite legs are the same, then this would be pi over 3 radians. This would be pi over 6 radians. There's a right angle. So the cosine of pi over 3 would be 1/2, and the cosine of pi over 6, right, this angle would be the side divided by my hypotenuse, and by the Pythagorean theorem, I know that's square root of 3. Okay, so the dot product is connected to the cosine. You should remember what the cosine function looks like. Another connection here, let's see, I just need a little bit of space here, I guess. Remember the unit circle centered at the origin. If you parameterize the unit circle, the x coordinate on the circle is the cosine, the y coordinate is the sine. So again, that gives you a connection. And if you think about what the cosine is going to be for the triangle as you move around, you get the graph of the cosine function. Right, so all these things are related to each other. They come back here. And does everyone have what they need from this page?
Can you actually go back to the last page for a second?
Sure.
Thank you.
Do you just need time to copy, or did you have a question?
No, I just needed time to copy, like, just one last thing. Thank you.
All right, just let me know when you're ready.
All right, all good. Thank you.
Okay, so so why is this important? Well, let's imagine you have the following situation. You want to know, say you have some body, let's say it's on a guide that forces it to move along a straight line. And let's say that you apply some force to your body or to the object. You want to know what component of that force is actually going to be directed along the path that the object can follow. So that means essentially you want to decompose your force into components along a certain direction and perpendicular to a certain direction. So you can say what component of an applied force is directed along the path of an object that's constrained to move along a straight line. So here's the actual force that you can apply. Let's say it's F for force. And you know that the work done in this situation is going to be the component of the force along the path, right? So it's going to be the length of that thing. So what you could do is, let's say that there's a vector D directed along the path of travel. You can actually get what you were looking for here as F dotted with D. Okay. So D here is the displacement vector. Right, so it's not just the direction of travel, but it is the actual, I don't know, let's say P to Q. We can say D is this path. Right, so the work depends on the size of the force that you're applying, the component, the size of that component that you're applying, and the distance over which you apply it. And what is this? Well, that's just the length of F times the length of D times the cosine of the angle in between. And that's something you can work out if you actually know the angle between these two guys, right? So you could try to measure that work directly, or you could just measure the force, measure the size of the force vector, measure the length of the force vector, can measure the length of the displacement vector, and you can look at the angle between those two. Okay, so work so tension in physics and engineering, and there's something that is important in certain types of mathematics. Practically, this was introduced in the context of navigation, which probably might be a little bit remote for people nowadays, but this idea is actually important in things like control theory and robotics. So it is still important. So the direction angles, I can't write. Alpha, beta, gamma. In 3 dimensions are just the angles that the vector makes with the 3 component axes. So alpha is the angle that your vector makes with the x-axis. So we can get our hands on that by dotting with the vector I. Use underbars for vectors. Remember that the vector I is a unit vector. And if my vector has components A1, A2, A3, remember that I had as components 1, 0, 0, J has got 0, 1, 0, K. It's got component 0, 0, 1. So this just picks out the first component, or the x component, and it divides it by the length of the vector. And the beta and the gamma work the same way. The beta is the direction angle with the y-axis. So that's going to be A2 divided by this guy. And the gamma is the direction angle with the z-axis. So that's going to be A3 over the length of the vector. Okay, so you can get your hands on the direction angles just by looking at a unit vector or that points in the same direction as your given vector. Right, so if you divide the vector by its length, you get a unit vector, and the components of that unit vector are just your cosines of your direction angles. Right, so look, notice what we have here. By definition, this guy, the alpha, well, that's the dot product of the vectors divided by the product of the lengths of the vectors. That's exactly the cosine of the angle that the vector A makes. Sorry, I should have put the cosines in here. Sorry about that. Okay, so make sure you fix that typo. So this gets your hands on the cosines of the direction vectors, from which, of course, you can use the arc cosine function to get the angles out. All right, so we're about at the end of time here. So thank you for your attention. We'll pack it up for today. Does anyone need more time to copy, or does anyone need me to go back in the notes? Everybody good? Okay, so I'm going to stop sharing. Thank you for your attention. I have office hours, remember, from 10 to 11:30 if you want to stop by, if you've got any questions. I saw many people have gotten started with the WebAssign. There's still a couple of people who haven't signed up on WebAssign yet. So if you're in that category, please hang out with me. Let me see if I can help you get your WebAssign sorted.
Thank you.
Don't fall behind. Okay. Thanks, everyone.
Thank you.
I have a question about the WebAssign.
Sure. Go ahead.
So you get the extra credit when you do it in advance, right?
Yes.
So I remember the way it worked for 242. I mean, it may not be the same. Was that your homework average could never go over 100%. But let's say if you got like 105 on one assignment or like and like a 70 on another homework, the 105 counted toward your homework average. Is that gonna stay true for this course or?
Yeah, that's how we do it. So the
Okay.
homework, you can get a bonus for early submission. So you can think of that as giving you a little bit of leeway. You don't have to get 100 on every assignment. You can even things out if you get some things in early, but
Gotcha.
it doesn't let you get your homework average above 100.
All right. Thank you so much. Have a good one.
You too. John, did you have a question? Oh, okay. Vaughn, do you have a question? Okay, I'm going to stop the recording.